So I'd like to introduce our first speaker. So this is Cyan from EPFL Switzerland. So take it away.
Hello. So yeah, I'm postdoc at EPFL, but this work that I'm going to present was in fact done as a part of my PhD at INRIA and École Polytechnique in Paris with my supervisor Katusha. And so as we all sort of know, at least in this community, that we are today our lives are basically entangled with various sorts of location-based services. And therefore lots and lots of data, location data are being shared, well, produced, shared, and collected and used for various sorts of analytics. On the other hand, as research and technology are progressing, it's also very concerning how there's a massive surge of a bunch of privacy invasive attacks which exploit lots of information leakage from such location data that are shared. So it's kind of universally acknowledged that it's very important to protect the privacy of the shared locations. However, it's also crucial to uphold the utility of the data for all the parties involved. That includes the user's utility, which is often termed as the quality of service, and that of the service providers, which is often termed as the statistical utility of the data. So in this work, we established Blahat-Hermot algorithm, which is like a very old information theoretical algorithm, as a prime candidate for comprehensive location privacy. And we exploited a bunch of different properties that we discovered of Blahat-Hermot satisfies, and we proposed an iterative method for collecting location data which optimizes which optimizes the triadic trade-off between the location privacy with the utility of the users and the service providers. So probably the only relevant piece of background that might be useful for following the rest of the presentation is the definition of geo-indistinguishability, which is basically a metric-based generalization of differential privacy, which was proposed a few years ago, and then it blown up. The popularity blew up because of a bunch of different good properties that it satisfies. Firstly, it's a formal standard of indistinguishability specifically catered for location data. It is, as I say, it's generalization of differential privacy, capturing the essence of ground distance between points. It satisfies all the good things that differential privacy does, for example, compositionality, and like differential privacy, it is independent of any side knowledge that's held by the adversary. And most importantly, it is rather easy to implement, and the canonical mechanism that was proposed as a part of the paper of geo-indistinguishability was local Laplace, and yeah, that was, until this paper, was considered the state-of-the-art for geo-indistinguishability, for guaranteeing geo-indistinguishability. However, in fact, the project started when we started finding out a major flaw in that Laplace mechanism, local Laplace, that satisfies geo-indistinguishability, in that it treats the strong, that is the crowded locations, and the vulnerable, that is the geospatially isolated ones, kind of equally. So basically, if you are spending a beautiful holiday in the Caribbean, and wanting to order some nice pizza around you, with a very high probability, an attacker who knows that you're on holidays will know that you're not looking for pizza whilst you're having a swim in the North Atlantic. So probably you are in Barbados. So hence it then we started investigating the problem a bit more. And now, a bit of a side note, Blahat-Hermot algorithm was proposed much before, in 1972, for completely different reasons. It's, in fact, a very famous algorithm in the field of information theory, for those who are familiar with it, by Richard Blahat and Suguru Aramoto, like independently, and it's mainly used for maximizing channel capacity in information theory. So we started looking at Blahat-Hermot algorithm because we found a prior work that, as a side note of the rest of the work, which was completely done for different things, showed that, by the way, Blahat-Hermot satisfies formal geo-indistinguishability. But that ended there. So we started asking questions like, can then Blahat-Hermot algorithm address the problems that Laplace cannot? How do Blahat-Hermot and the state-of-the-art for geo-indistinguishability compare in terms of utility? And can we use Blahat-Hermot in a sense? Can we furnish a mechanism that optimizes this three-way trade-off between privacy and utility? And first things first, we very quickly observed that, in fact, the problem of isolation is solved. So on a high level, what Blahara model does is, as opposed to Laplace, it obfuscates the locations, not around the true location kind of uniformly, but from the most crowded area to the second most crowded area, and so on and so forth. And eventually, it converges to that of Laplace. So that was done. Then we started looking at the statistical utility of BA and Laplace. And for that, we used something called iterative Bayesian update, which is basically an iterative expectation maximization technique in statistics. And the distance between the true prior and the estimated prior is often termed as the statistical utility of a privatizing mechanism. And under this, we showed that Blahara model, in fact, has a substantially better statistical utility for high privacy regime than Laplace, and eventually they become comparable. And we went on to discover another very intriguing property we could show that Blahara model algorithm and iterative Bayesian update, which, again, remark, were discovered at very different times for very different purposes, addressing very different domains of mathematics, information theory and statistics respectively, are dual to each other. So you can basically get one from the other. I mean, as a mathematician, I love discovering properties. The work could have ended there. But we thought we want to discover something more, or probably use these properties to furnish something more useful, which might solve something in location privacy. So that gave birth to Privic. For the sake of time, I shall not go into detail of the working of the algorithm. Basically, it's a very sly way where we iteratively used Blahara model and IBU to sort of like furnish a three-way optimal mechanism in the end. So whenever you do something iterative, and whenever you are a mathematician, first thing you want to do is prove convergence, which we did. And second is you want to do experiments to show that your proof is not absurd, which we did, on various kinds of location data. And then we, in fact, wanted to see how good is this limit. And we showed that, in fact, we are getting quite a good estimate of the true prior under our mechanism, which basically means that we are getting a very good statistical utility. And we further showed that as a limitation, like under an adversarial setting where, let's say, adversaries are adversarial users who have no interest in complying with the mechanism are starting to report their location like faking them, dumping them in a really isolated point where honestly, genuinely isolated users are situated, then our privacy guarantees are at least as good as Laplace. So even like under an attack, we are providing privacy guarantees, which is not worse than the state of the art. So in summary, we showed that a bunch of different good comprehensive privacy properties of Blahara model compared to the state of the art. We exploited, I do not know what happened. Oh, oops. I do not know what happened. Turns out I received a call. Yeah, and we showed that we have a bunch of different, we exploited these properties to propose our iterative method for collecting location data, which we showed to be formally gender distinguishable and more. So it satisfies gender distinguishability and protects the isolated locations. It optimizes the quality of service of the users with respect to their privacy from an information theoretical perspective. It harbors a very high statistical utility for the service providers, and it provably converges. And I'd like to thank my PhD supervisor, Katusha, and funding is always good. So YASI Advanced Grant for supporting the work. And thank you.
So do we have any questions for the speaker? I was wondering about the computational cost of this. So does it compare sort of favorably, or is it more expensive, less expensive than prior work?
This is actually, yeah, it is more expensive, because there are two different iterations going on. One is both are iterative algorithms, Blaha-Dermoto and iterative Bayesian update, and we iterate high-level iteration over them. So computationally, it is expensive, but prior work, in the sense Laplace would exclude the Blaha-Dermoto part of it. So, but the IBU will still be there. So yeah, it comes at that's a trade-off. Yeah.
Okay.
Yeah.
I mean, further to that, could we have like a Pareto frontier where we're trading off sort of the computational cost versus the privacy and sort of pick where we want to be on that frontier?
Yeah, so basically, the more you do Blaha-Dermoto, the more you head towards the convergence, and the optimality will be achieved in a better sense. So in theoretical realms, obviously you go towards the limit. But in practice, obviously you go up to the accuracy you want to achieve out of the optimality. So yeah, in the paper we showed that as optimal you want to get, you can go up to that point, and then it's kind of, yeah, it's a user's choice. Yeah.
Hi, thanks for the talk. I might have just missed it, but I was curious, in the convergence plots, you see earth movement resistance go down to 0. I was curious what the two distributions are. Like what's
the true prior, so the true prior and the estimated prior. So yeah, sorry, I didn't go into details of iterative Bayesian update. So it is basically a way to estimate a secret prior with the knowledge of the privacy mechanism and your observed privatized observations. So then what you get is this P, which approximates pi essentially, or approximates in the sense it gives you the maximum likelihood estimate of pi under the observations. And the distance between this estimated prior and the true prior, which is unknown, obviously, is we used earth move resistance to compute this.
Okay, but in real life, what does the pi represent?
The prior is like the user's distributions, right? So
okay.
like your data, everyone's data.
Okay,
that is secret. Yeah.
Thanks.
Any other questions? No? All right, thank you. If we can thank our speaker again.